In 15.7 part 2, we are going to use that idea, the divergence theorem, and we're going to apply it to a couple examples, and these are examples from the book. Example 1 says, let Q, we use Q a lot of times, or E for some kind of a solid region. Let Q be the solid region bounded by the coordinate planes and the plane 2x plus 2y plus z equals 6. Your vector field is x comma y squared comma z. And we're finding the double integral of f dot n ds, or otherwise known as flux, if S is the outer surface of this solid, and we're going to use the divergence theorem to do this. So let's first find what this solid looks like. Okay, so if we draw the x, y, and z plane, so it's solid bounded by the coordinates plane, the xy plane, the xz plane, and the yz plane, and this thing. So when x and y are 0, z is going to be 6. When x and z are 0, y is going to be 3. And then the x-intercept is here. Okay, so this is our solid right here. It's a tetrahedron. There's this side of the solid. There's the bottom, that triangle. This back triangle back here to the left, and this triangle over here. Okay, so the divergence theorem says we can calculate double integral of f dotted with n ds, and that should be equal to the triple integral of the divergence of f dotted with, not dotted with, times your over the entire volume, dv. This is over Q, and this would be over the surface. Now, if we were going to evaluate this directly, we would have to do this over 4 surfaces. We'd have to do the double integral of f dotted with n ds over S1 plus double integral of f dotted with n ds over S2 plus double integral of f dotted with n ds over S3 plus the double integral of f dotted with n ds over S4. We'd maybe define this front surface as S1. Maybe the bottom is going to be S2. Maybe this left surface and back is going to be S3, and then this back surface over here that lies on the YZ plane would be S4. And we have to do all 4 of these differently. Notice your normals on each of these surfaces are going to be different. Okay? But if the question tells you use the divergence theorem to calculate this, we don't have to do it directly. Instead, we can simply find the divergence of f and find this, the triple integral of the divergence of f. And remember the divergence of f, it's the d dx, d dy, d dz, dotted with your f. The f is defined as x, y squared, z, over your entire volume. Okay, so that this dot product, or the divergence of f, is going to be the x derivative of x, which is 1, plus the y derivative of this, 2y, plus the z derivative of this, which is 1, over the volume, triple integral of 2 plus 2y. The volume, we could do dz, dy, dx. Z is going to go from 0 up to the z value of this surface, which is, you can solve this thing for z. Z equals 6 minus 2x minus 2y. So z will go from 0 to 6 minus 2x minus 2y. The y will now go from, well, now we've got to project this thing onto the xy plane. On the xy plane, the x-intercept is 3, the y-intercept is 3. Okay, so this thing we could call y equals 3 minus x. So y will go from 0 to 3 minus x, and x will go from 0 to 3. Okay, let's take the antiderivative with respect to z. So you've got 2z plus 2yz as z goes from 0 to 6 minus 2x minus 2y. So that's going to be 2 times this thing, so we'll do 12 minus 4x minus 4y plus 2y times z. 6 minus 2x minus 2y, and then minus, plug in the 0 for z, so we get minus 0. Okay, so we've got 12 minus 4x minus 4y plus 12y minus 4xy plus, minus 4y squared. Combining like terms, we've got 12, 4x, so minus 4x plus 8y minus 4xy minus 4y squared. And we're integrating that with respect to y, and the y went from 0 to 3 minus x. Okay, so we've got 12y minus 4xy plus 8y squared over 2, so 4y squared minus 4xy squared over 2, so 2xy squared minus 4y cubed over 3, as y goes from 0 to 3 minus x. Make sure you can see that. Oh, this one's going to get a little bit messy, but we've got 12 times 3 minus x minus 4x times 3 minus x plus 4 times y squared. So this thing squared is going to be 9 minus 6x plus x squared minus 2x times 9 minus 6x plus x squared. And then we've got minus 4/3 times this thing cubed times, we need 3 minus x cubed, which is 27 minus 27x plus 9x squared minus x cubed. Okay, distributing and simplifying. We've got 36 minus 12x minus 12x plus 4x squared plus 36 minus 36x plus 4x squared minus 18x plus 12x squared minus 2x cubed minus 36, now here, 36 plus 36x minus 12x squared plus 4/3 x cubed. Okay, bear with me for a second. This right here, when we did this times this, 4 times 9 was 36, 4 times negative 6 is not negative 36, that's negative 24x. Okay, so now I'm going to come over here. I'm going to combine my like terms. The constants add up to the 36, 36, and 36, so we've got a 36. The x's add up to negative 12x, negative 12x, negative 24x, 18x, and 36x adds up to negative 30x. The x squared, 4x squared plus 4x squared plus 12x squared minus 12x squared is plus 8x squared. And then we've got negative 2x cubed plus 4/3 x cubed, which is negative 2/3 x cubed. Okay, we have to integrate this from 0 to 3 with respect to x. So I've got 36x minus 30x squared over 2, so 15x squared, plus 8x cubed over 3 minus 2/3 x to the 4th over 4, so that's going to be x to the 4th. It's going to be 1/6, and I have to evaluate this from 0 to 3. So 36 times 3 is 108, minus 15 times 9 is 15 times 9, 135, plus 8 times 3, so 8 times 27 over 3 is going to be 72, minus, and that's 81 over 6, also known as 27 over 2. Okay, so 108 plus 172 is 180. 180 minus 135 is 45 minus 27 over 2. So we've got 90 minus 27 all over 2, which is 63 over 2. Okay, and yes, this got messy, but really doing that triple integral of over the entire solid was better than doing all 4 of these separate surface integrals.